Hello everybody. I'm Danko from Evo Center. I will be talking about the artificial intelligence, problems of scalability and sustainability. We have just heard about sustainability in a previous talk, and there are different aspects. And the aspect that I will talk is a little bit different because I will talk about the artificial intelligence, whether we can build more intelligent machines, and that these machines are scalable and sustainable. So these are the topics, the points that I will make. AI technologies today does not scale well, and it may become an environmental problem over time. On the long run, it's not sustainable. And I will also talk about the ways out. What can we do to make it better? And so think about this robot. That's our goal. Maybe in 50 years, 20 years, 100 years, we'll have one at home. But the question is, how are we going to make all the intelligence necessary for such a robot that can take care of a household and yet not to spend too much energy and yet to be sustainable in terms of the size of AI. That's all we have today. So we have lots of work to do, right? Now, here's a question maybe for people in the audience. If you plot on x-axis intelligence of AI solutions that you have seen today, heard about them, and so on, and on the left you have resources needed to create this AI, needed to run this AI. What do you think the curve looks like? I know because of noise you cannot speak. Then you can just think, or you can make in the air a curve. You can draw the curve, what you think it looks like. And if you don't know, I'll show you. Yeah, I see some hands. I'll show you curves that we found. Right. So this is a curve how the size of the models grow in the MNIST task. Right. So you get small models for some performance, but if you want to get a last few percentage of performance increase, you need to get really big, huge models. It actually explodes. The size of the models keeps exploding. Right? Here is one study, much more careful study that looked at the ImageNet models, their performance and their sizes. And as you can see, as the accuracy increases, you need bigger and bigger and bigger models and more parameters, more floating point operations. Right? It's, again, exploding. Right? Here's another study that was behind the GPT-3 that has shown that the model performance keeps increasing. Here you see it by test loss reducing. But you can add parameters and you can add the data science to keep increasing. But the problem is that these are all logarithmic graphs. It means that every time you need to increase, for each new step, you have to increase much more the amount of effort, the amount of data, the amount of computation, the number of parameters. Again, it's increasing. And people have studied it and found that it's actually power law. It's a power law function. And it's not good. It's not sustainable. Power laws functions are not sustainable, right? Now, you can see that if you remember, the best state-of-the-art models that everybody was talking about. Which machine did you need at which stage in the history of AI to run these models, right? In the 90s, it was enough to have a PC. You could run the state-of-the-art models. Then in the 2000s, you needed to buy a GPU. Then later, you needed to have a farm of GPUs to run a state-of-the-art model. And today, the best models run only on the supercomputers, right? So the question is where are we going from supercomputers? We don't have anything better. So where's the future? What are we going to do next, right? It's exploding. It's really exploding, right? And these supercomputers, of course, require lots of electricity. Now, more details about these explosions and so on you can see in our book that just recently came out. That's an excellent book it's a handbook on data science, all about data science, and one chapter about AI is explaining why you have this problem, why this problem exists on the first place. Right? And that's not what we want to have. We don't want to have a robot in the future connected to supercomputer and to power plant in order to be able to clean a house. Doesn't make any sense, right? So what we want to do in the future, we want to have artificial intelligence solutions that run on a little battery instead of a huge power plant. Here's, for example, here on the bottom, you see calculation for a GPT-3 model. Somebody has estimated that it spent about 1.4 gigawatt hours to train it, which is with a price of 30 cents per euro, amounts to 420,000 euros just to train this model once. Right? So what we want to do in the future is make things smaller, not bigger. We don't want a bigger models. We want them smarter, but not bigger. We want them smaller. Right? Now, this is a similar example with the technology of engines, like the steam engine, the first one on the left, and the later, if you don't change the technology, you just make things bigger, right? But there is a solution with a different technology, which when you see on the right, the little engine that has only 11 centimeter size, right? And it's almost as powerful as the huge one on the left. It's actually the size of his shoe. And he has two shoes. If you had two such engines, you basically get more power than you have on the left. So we need a new technology. Here's also, electric motor that's maybe this size that produces the same power as this huge engine. Right? So make things smaller. How are we going to make things smaller and yet smarter? Right? So I will basically tell you 3 ways how to do it. The first one is to specialized machine learning model, again, described in this book. And this reduces the exponent of the power law. So how do you do that? So you know that deep learning is a general model. It can kind of learn anything. And it's exactly the price you pay. If it can learn anything, it's going to scale really badly. If you build a machine learning model out of equations that are suitable exactly for the problem that you're solving, you can make a miniature model, and it will work. And it will reduce the resources. And we have done that. I have done that successfully in the past, where we have building a model based on financial mathematics. So we didn't put ReLU function in, but we put concepts from financial mathematics in it and build a machine learning model. And it worked wonderfully. And one advantage was that it had small amounts of data. It required really small amounts of data, right? So do not use deep learning if you do not have to, if you want to go scale, right? In other words, generic machine learning is a wasteful machine learning. In terms of, it's just kind of lazy machine learning. Just put lots of data, lots of computational power, you don't have to think. In a way, it's lazy machine learning. Second way, adopt GoFi. How many people know what GoFi means? Raise your hand, please. This stands for good old-fashioned AI. And a good old-fashioned AI was basically the first version, the first generation of artificial intelligence that was developed somewhere in the 50s and 60s and so on. Right? And it's also called, better known as symbolic AI. Now, today we make fun of GoFi. And we glorify machine learning and deep learning. Right? There's lots of jokes around, like AI in the background, it's only if-then statements, ha, 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 right? And that's kind of a joke about GoFi approach, which was based, largely on if-then statements, right? But you may not know, but every large AI solution that you have today, every cool AI solution, has a lot of GoFi in it. A lot. It's just not advertised because it's not cool. The machine learning part is advertised, but the GoFi part is hidden. But the thing wouldn't work without the GoFi part. Right? Now, another interesting thing, a great thing about a GoFi, it's much better scalable, and it's much better sustainable. It requires so much less resources. It's not wasteful, not nearly as wasteful as deep learning in terms of energy, in terms of computational power, in terms of data, right? It requires human thinking because humans are building it. It's not machine itself building. It's humans have to think it through. But once you got it, it's very efficient. It's very, very efficient. Faster, effective, and so on, right? Oops, wrong button. So one example I have here is a Monte Carlo search algorithm. This Monte Carlo search algorithm is in AlphaGo. You heard for sure about AlphaGo, how machine had won against the best player of Go, the game of Go. So the machine is the world champion. And I think the score was 4-1. Now, also chess games, similar story, right? Now, you've heard of the machine learning part. There's an awesome machine learning, deep learning model in it. And yes, it is. But also, who is controlling the machine learning? Who is deciding which kind of, what for the next decision will this problem will machine learning model try to find a solution and so on? Is this algorithm? It's a GoFi algorithm. It's an old algorithm that's used for the first chess games even before machine learning was introduced, right? So it's a combination of the two, and it's always every great AI solution has a combination of the two. And you can, as a designer, you can make a decision and put more emphasis on machine learning or more emphasis on GoFi. Right? And if you put more emphasis on machine learning, you will need more data, you will need more computational power, you will need more energy, and so on. Or, instead of this, you think, you engineer, you study, you understand, you design. What you get is a more effective, a better machine. And that's what basically that's how we make progress. Right? In machine learning, we come up with new combinations, new architectures, new steps of processing, and all this together is basically a combination of GoFi and machine learning. You're reducing the machine learning, the dumb, heavy component of machine learning, and putting in the architecture. Right? So here, who knows what this AI architecture? Can anyone recognize this one, what that is? Well, this is IBM's Watson, the one that won the game of Jeopardy, right? So again, example. You have lots of components. Each of these components, many of these are machine learning, some are not, some are. But the entire architecture is actually something that was well thought through and took lots of time, lots of thinking, lots of research to get it right. And the architecture itself is also the GoFi part of the entire solution. So every single thing, every big thing has both components. Don't forget that. Right? Now, at EvoCenter, we are also combining the two. We are combining deep learning with GoFi to develop our solutions to return calls as customers, right? So when people call a company and they need something solved, they can first talk to AI. Now, there's lots of useful things that you could do with deep learning, but there's lots of things that deep learning just cannot handle because it would require so many data that we cannot access them, or we cannot possibly have them, or we could not have computational power to calculate all that. So we have to combine the two. Right? And we are basically developing an effective approach on how to very quickly add new GoFi components, like really quickly. So when you have a new idea for the architecture of the AI solution, you can instead of spending 3 months of changing architecture, you can change it in 3 hours and expand the intelligence and the effectiveness of the whole system, right? Okay, so this was the 2, and here's the third solution. The hardest one to do, but we will have to do it one day. We have to make AI do it like the human brains do. And so the brains use just a little bit of energy, right? 372 watt-hours per day. For example, GPT training, then if you take the energy GPT training used and human brain is 10,000 human years just to train once a GPT-3. Right? So that's the relationship. And yet we are smarter than GPT-3, more intelligent. Right? So the question is how? How can we do that? How can we build AI that's actually as effective as that? And also animals, the same thing. Right? Animals are also super smart in the domain in which they are smart, in which they need to operate to survive, and work in the same principles like a human brain. Right? Now, the same plot that I had at the beginning, we have intelligence and resources, but now the question is, what do they look for human brain? Like I've shown you, we have seen that for deep learning it's just exploding power law function that's really ugly and not sustainable. What does it look for human brain? Well, it's very nice. Learning is pretty much a linear function. Right? So if you learn some new thing, you need the same amount of resources as from the previous thing, right? Some things are more difficult to learn, some things are less difficult, some require some pre-knowledge, of course, but still, if I give you a new fact, you have heard some facts from me, you have heard facts in another talks, you talk to a friend, they tell you something, you learn information, and each of them requires approximately the same amount of effort to add a new piece of information. That's linear. And that's not how deep learning works. Deep learning, if you want to add new information to deep learning, then you have to get all the previous data, retrain the network, and as a result, every new additional learning requires more effort than the previous learning. And you get this exploding curve, right? And human brain works somehow much better. But then there's even a much better thing. 5 minutes, thank you. Flat application. That means that it's even better that once we have learned that, we can use this new piece of knowledge, apply it immediately to so many different applications, to so many different cases, that deep learning cannot. Deep learning needs all of these examples to be able to apply it. And we just get it once and we apply it just straightforward, right? So that's really efficient. That's really efficient. Here's an example. I'll give you an example. I will teach you something new very quickly. And I will teach you that that's how we now draw cars. Easy, right? You just, boom, you got it. AI cannot get it. You need a million examples. But here's how you can apply it. Really great. The flat line. Now, the flat line is, I draw this and ask you, what's that? If that was a car, what's that? Is it a truck? Yeah, it's obvious, right? And what is that? That is a train then, right? Now, I'll show you just a sec. I'll show you just a moment. I'll show you the same thing. Real learning, like amazing real learning. Now, I tell you, no, that's not a car anymore. Now, this is the way how we draw tables with chairs. Boom. In a moment. It doesn't take longer now to learn that from the previous fact. It's just linear process. Now you can apply it here. What's that? Yeah, I heard something, school or restaurant or something, right? Here's a school, right? Even better, right? So you can reorganize things really quickly. Our brains are so flexible. Deep learning is like not even closely there, right? So the question is, how is that possible? It's difficult, it's complex. I have, who is interested in more, I have some ideas for AI, how it's going to do in the future. You can go and read this paper or take a photograph of this paper. Okay, yeah. Back for more photographs, please. You can take my picture with it. Okay, everybody. No, one more. Okay, good. So, conclusions. What did we learn? No, it's not conclusions yet. There's a couple more things I want to say. So we are developing a technology for making deep learning smaller, and yet smart. Not bigger, but smaller, right? So you have parameters in it that are just normal network parameters, but then you have another set of parameters where the deep learning learns how to learn a certain domain. And so what we achieved with this is that we get fast learning, 100 times faster than usual, because it knows how to learn, just so quickly learns things. We also were able to produce one example of learning, like I did just now. Just give one example, it can generalize quite well. Not like humans, but better than other. And what we are working on is on reconstructive or constructive recall of information. Now that's how we humans store information. We don't memorize details. We just memorize a few little things, and then when we try to remember something, recall something, we reconstruct it. And that's how we save all this energy. And that's also how we get all the flexibility in thinking, right? Okay, we call this guided transfer learning as opposed to classical, traditional transfer learning. Okay, so making things smaller, not bigger. AGI. I want to talk about AGI briefly because somebody talked about AGI today already during discussion. So the question is AGI, what is are we ever going to have AGI, right? I think not, but maybe, who knows? But the problem with all the AGI proposals today are that they have the same problem, the non-scalability problem. They demonstrate something on a small scale, and they don't do such plots. If they did such plots, most likely you would get curves like this. And if you have curves like this, it's not general. It just can't scale. It's not sustainable. You cannot have a computer bigger than supercomputer. So it's not going to work unless you can show this curve. So task for AGI people is to show these curves. Plot these plots and show something flat or linear or something like that, not exploding curves. Okay, so here's my conclusions. We need AI that scales well and is sustainable. If we want to increase the intelligence of AI and have really smart machines, like really, really smart machines. Deep learning is not that, doesn't do the job. It's actually worse, it's horrible. We need some new technologies. It is in principle doable, we know for a fact, because human brain can do it, so therefore in principle it is doable. It's not easy to figure out how. So please plot your scalability graphs. All of you who claim to have created some new amazing technology for machine learning, plot the scalability graph. Let us see how well this scales. And admit problems. If it doesn't scale well, tell it to the world. It doesn't scale well. Right? Think sustainable. Thank you very much.